All right, so today we're going to take a look at some more exponentials. And the exponential rules we're going to look at today are going to be very similar to the one we had before. The difference is we're going to have different bases now. So we don't always have a base of e when we're working with exponents. So we need to know what happens when the base is not e. So let me talk first about those kinds of functions specifically. If we have a function, or if we have the letter a, okay, so a is a number. A is actually specifically a real number. Sorry, that's for another class. So you've seen that notation before? I think we talked about it once already, didn't we? A is a real number. And you can't have a equal to 1. It's the only thing it can't be. Okay? It's bigger than 0. I shouldn't say that. It's bigger than 0. It's the only positive value it can't be. Then the exponential function with base a is a to the x, defined as, so what is a to the x? Well, a to the x has actually this definition. It's e to the ln of a times x. And I bring that up because that's going to sort of give way to why we get the derivative that we get. So when we work with this one's derivative and antiderivative, it's coming from how this function is defined. And if you take a look at that e ln a business, that is actually equal to a. Right, that's a property of logarithms that was from algebra somewhere along the way that you saw. Logarithmic functions, same idea. The a value can't be 1, and it's a real number. So real number not equal to 1. What would happen if it were equal to 1? Let's go back to the exponential. What happens if I had an exponential with a base of 1? What would that look like? Straight line, right? It'd be 1 to the x, and anytime you try to raise 1 to a power, you get back the number 1. So it wouldn't be an exponential, it'd be a horizontal line. That's why we're sort of excluding that possibility, is because it's not really an exponential when we do that. So the logarithmic function with base a is log base a of x, like so. And log base a of x is defined as 1 over the natural log of a times the natural log of x. Or you could write this, of course, as natural log of x divided by the natural log of a. And if you did that, it would look like something called the change of base formula that you learned in a calculus or in a college algebra kind of course. Change of base formula. All right, so let's take a look at some properties. We've seen these properties before, but, well, let me say first, the logarithmic properties. All those properties that we did before about taking logs and adding two different logs together and being able to combine them back with multiplication, and taking two logs that were subtracted and combining them back in with a division or expanding them out, or taking exponents and making them coefficients, all those properties still apply to logs. Okay? Some inverse properties, though, that relate these two kinds of new functions, if you will, that we're talking about today together, is that y equals a to the x. Have you ever seen IFF written? My daughter would probably tell you I misspelled something.
If and only if.
If and only if. IFF means if and only if. And you got that from Dr. Marsh, didn't you? In linear algebra. Yep. IFF, if and only if. If and only if x equals log base a of y. And we had a very similar description when we had e to the x. We said y equals e to the x if and only if x equals natural log of y. So this is the same inverse property relationship. If we have a raised to the log base a of x, this is equal to plain old x. Kind of the idea of the a and the log base a canceling each other out. They're inverses of each other, so we get back the same x. And this is true for all x that are positive. So that upside down a means for all. Doesn't it?
Yeah.
It does. It's on your sheet, I promise.
We use that a lot.
A lot. Here's another one. If you have log base a of a raised to the x, and again we saw a very similar one of these with natural logs, then let's see what would happen. Well, properties of logs say that this x could come down here in front, correct? And then what do you suppose log base a of a is? No guesses?
A.
Nope. Nope. The x has been moved. It's not here anymore. It's in the front. So what's log base a of a? It's 1. It's 1.
Next guess would have been
You should have known it's 1 because we did this with ease. We did one that said, well, let me write down this one first. We did one that said the natural log of e. What is the natural log of e? Oh dear. It's 1, right? The natural log of e is 1. But what is natural log? Well, it's log base e of e. Well, this is log base a of a. Same property, all right? So this equals x. Again, this is for all x. That's that upside down a, for all x that are greater than 0. Why does x have to be greater than 0 in both of these guys? Do you remember? You can't take what? Right. You can't take the log of a negative value, right? That's undefined. Okay, so logs always have positive input. So we're looking at putting these as input on a log, or nearly so. Because the second one for sure, an input on a log, we can't have a negative value. Okay, so we're going to do some examples. Again, just this kind of like what we did in section 5.4, but we're going to do it with basic, any kind of logs now instead of specifically natural logs, and any kind of bases for exponentials as well. So here's our first one, and I talked to you guys last time about a bug. What kind of bug did I talk about? A scorpion, didn't I? Yeah, we're going to do that guy again. So you're going to circle the B, that's the base, and you're going to draw the scorpion tail all the way around until it lands with an arrow on the number that's beside the log, the input for the log. And we're going to rewrite this as an exponential. So the B is the base for the exponential. The 3 on the other side is the exponent for the exponential. And then this equals where we landed, which is 27. This turns us into an equation that you guys have dealt with a fair bit. How would you handle this? How would you solve for B? Cube root. Cube root of 27 is 3. It's 3. The decimal says accurate to 3 decimals. Obviously, I don't need any on this one. Yeah?
Yeah, for these kinds, if it's simple like that, do we have to write down the second step on there, or can we just say that B equals 3? Because I did that.
Most of them aren't going to be as simple as this.
True, but if they are that simple.
If they were super simple like this, Emily, and you
Yes.
did it, I'm not going to complain too much if you can do the harder ones too. How's that?
Okay, sweet.
Okay. I don't think that you can do this one without a little bit of work, though. Probably not, right?
Right.
Okay. I see that we have something added together. 2 logs. So I can combine them. How can I combine them?
It's log base 3 x times, in the parentheses, x minus 2.
Something like that?
Yeah, something like that.
Something like that. So that's a property of logs. It was a property of natural logs. It's also a property of logs. And then once I've gotten it into this form, I can turn it into an exponential, right? So I circle my 3, and I'm going to draw my circle around. Draw the circle, don't draw the circle, I don't care, but that's how I think about it. So we're going to take the 3. We're going to raise it to the first power because that's on the other side of the log. And then this is going to equal the x times x minus 2. What's 3 to the 1? 3. Please do not be tempted to set the x equal to 3 and the x minus 2 equal to 3. That's a very common algebra mistake, but you guys are not in algebra, okay? So I really don't want to see that. This right here, if it were set equal to 0, you could set each term equal to 0. Agreed? Mm-hmm. Yes. But this is not set equal to 0, okay? So we actually have to multiply this out, which will give me x squared minus 2x. And then how do I deal with this now that it's a quadratic equation? We want to unfoil. Okay, so we want to factor, right? And in order to factor, I first need to move the 3. So this 3 needs to move on the right-hand side. So this is 0 equals x squared minus 2x minus 3. And then, like Kendra was getting at. We want to make this in factored form. Okay, so how do I factor x squared minus 2x minus 3? Right. Okay, so real quick reminder on factoring. The first terms here, x and x, those have to multiply to give me x squared, so you can get those in there without any work, right? The last two terms have to multiply to negative 3. Well, there really aren't a lot of choices. There's 1 and negative 3 or negative 1 and 3, so we got to pick one of them. If we've picked correctly, the inside term, negative 3x, and the outside term, positive 1x, should add to negative 2x. If they don't, then it means you've picked incorrectly. In this case, we only had two options of what we could pick, so all it would mean is that we had our signs wrong. Okay, so this is correct. Then what would I do? Now you can set each of them equal to 0. So now I have x equals 3, and I have x equals negative 1, right? You need to be careful not to stop too soon on these problems. This is the solution to the quadratic equation that I created, correct? But it may or may not be the solution to the original log equation that I had. So what you actually have to test for is you have to test to make sure that both of those x values are proper inputs for the logs. So starting with x equals 3, is it okay to have log base 3 of 3? Is that possible? Sure. In fact, you know what it is. It's 1. Okay, so that one's fine. Can I have log base 3 of 3 minus 2? 3 minus 2 is 1. Can I have the log of 1? Sure, that's fine. So x equals 3 is perfectly fine. But what about negative 1? Not okay. What's wrong with negative 1, Cameron?
You get negative well, on both.
On both, actually, don't you? So this is a double whammy. If I put a negative 1 inside the first one, log base 3 of negative 1, that's a problem. Why is that a problem? I can't have the log of negative numbers. And we looked at a graph that showed what the log graph looked like and all that kind of stuff. This is one of those issues. Okay? So if you were to have this, you could label this as extraneous. Do you remember that word? I'm running out of space, but pretend it says extraneous. Which means this is actually not a solution to the original equation. The only solution ends up being x equals 3. And you might have remembered there's one other time when you got extraneous solutions. It was when you were doing rational functions. And sometimes you end up getting numbers that make denominators equal to 0. So extraneous solutions typically end up being values that the input can't be. That's the issue. You look back at the original equation and say, is that an allowable input for this function? And in this case, x equals negative 1 was not. All right, let's take a look at number 3, or problem C, I guess. All right, on this one, does anybody know, I should offer bonus if you know, but that may not be fair. Do you know what this is, this equation? It is a form for something you have seen before. Cameron thinks he knows.
Money.
It has to do with money.
Interest.
Interest. There you go. This is a compound interest formula. Specifically, it's a compound interest formula. That 0.10 up there, that's an interest rate of 10%. What is the 365 meaning?
A year.
That's the number of days in a year, so this would be daily compounded. And why would it be set equal to 2? Do you remember when that happened in that situation?
Yeah, it's been years.
I know. You did it when you looked for doubling time. How long it took some investment to double. So that's where this is coming from. And you have seen this, again, it's a college algebra thing, right? You saw this in college algebra, and you had to have some way of solving because the exponent is where the variable is. All right? So there's lots of ways to handle this. One of the things you're going to want is to grab your calculator, and your calculator is going to be wonderful for keeping track of all your decimal points without you having to write it down. So grab your calculator. What do you think you might want to do first? What kind of simplification can you do?
Solve the inside of the
Right. Simplify, right? So if we actually take the inside and we take our calculator and we do 1 plus 0.1 divided by 365. And you can write down several decimal points. No matter how many decimal points you're going to write down, it's not going to be enough. So you're going to keep your calculator to keep all those decimals put without moving them. But if you just write them down here, I have 1 point something. I'm going to write down all the decimals that I wrote down. You guys can tell me if your calculators match. I have 3 zeros, and then I have 2739, 726. Do you have a nod from anyone? Is that what you're saying? Kendra's does. Aaron's
Does it matter
does.
if it's like 733, just round it
Yeah,
up?
mine says 7.
Oh, 7.3 at the end?
Yeah.
No, your calculator's going to keep it put anyway, so just let your calculator rest. And then we've still got the 365 out here to the t equals to 2. What do you think you might do next? Is there any other simplification you can do before we invoke logs? Because we're going to invoke them here pretty quick. Okay, let me show you a simplification you can do, or tell you one that you can do. Do you know one, Dylan?
Would you want to make the 365T on the other side so it's with the 2? So
Okay, so you can do that after you get logs involved. Yes.
Okay.
So there's 2 different ways you can go from here. Way number 1 is that your calculator has an expression that's really long and ugly like my screen, right?
Mm-hmm.
If you want to right now, you can raise this to the 365. Couldn't you? Sure. I mean, you're still going to have a t up there. You can't do anything about the t, but you could raise this to the 365. Yeah?
Mm-hmm.
Okay, so that's one option. Option number 2 is you could go ahead and do logs right here as well. Okay? I'm going to go with the logs right here just so that I don't have to do another simplification at the moment. If I put in logs, you can choose whatever kind of logs you want. Natural logs work as well as anything, so I'm going to put in natural logs. What does my property for natural logs allow me to do on the left-hand side? You betcha. 365t comes down to the front. I still have this ugly natural log, or an ugly decimal anyway. And I have a natural log of 2 on the right. Now, how am I going to solve for t? How will I do that?
Divide by 365 and line up that.
You betcha. So the 365 gets divided, as does the ln of 1.0002739,726. And I don't normally do this, but to avoid having to write it out twice, I'm going to write it as division on the whole thing. You know you have to divide both sides, right? Yeah. So I'm left with t on the left-hand side, which is what I want. And my calculator can do all the wonderful operations that you see here. So I'm going to actually show you a cool feature of your calculator that you may not have known, because now's as good a time to show you cool features of calculators as any, right? Okay, so you've got this ugly expression in here. Let me get the ugly expression in my calculator. Yes, we are. So you got an ugly expression. Mine ends in 3 as well, by the way. There's a button on your screen that says STO. It's above the on button. You see STO? Hit that STO button. It will take the answer, the long ugly decimal, plus all the decimals you don't see. Okay, the exact value now is going to be stored. You have to store it in here as something. I'm going to store it in here as x because it's the easiest variable to hit. So hit the x. Now, anytime you're on this screen and you press x, it's going to recall this stored value until you store something else some other time. Okay? That's good because now we can actually do the other parts. So you can type in ln2. You can even press enter if you want to, but you've got ln2. I might as well. I'm going to press enter. And then I'm going to divide that. Now, be careful here, because when you divide this, you need to divide it by parenthesis 365x. Don't just divide by 365x. If you do, it will divide by 365, and then it will multiply it by that x value you just got. Your calculator understands order of operations. You want parentheses around that denominator. Okay? When there's no order of operations, it goes left to right. So if you take the natural log of 2 and you divide it by 365x, after you've stored the x, and you hit enter, it will give you some number. It's not the number I have written down. That's not good.
Did you forget to do the natural log of x?
Oh, I did. I didn't get my natural log of x in there. You are absolutely right. We'll try that again. All right, we're going to take my ln2. Thank you, Dylan. Divide by 365 ln x. And the 365 ln x is all in parentheses. You even found that without seeing my calculator screen. That's pretty good. Well, that looks like a much better answer.
About the natural log.
I was talking about it. You're right.
I
So
mean, I guess you could have done the natural log of that number and then
stored that as x. You could. That's true. So another thing to do, Dylan has said, and he's right, is you could keep this in here, and without storing that as x, you could put the ln of that and store that value as x. That would have worked as well. I'm getting t equals what? Rounded to 2 decimals. Or 3 decimals. I think 3 decimals is the direction. So 6.932. This problem didn't have context, but we talked about what the context really is. What would it be? Years. So it would take about 7 years for this money to double if you put it in an account with these conditions. All right. Any questions on this? Okay. Just again, as like the last section, we did a little bit of algebra to remind you how the algebra works for logs and exponentials. We're going to do derivatives. So do you remember the conditions again on A? A is bigger than 0. What else? You've written them in there. A is a real number. What else?
A does not equal 1.
Can't equal 1. If that's the case, we've got a couple of derivatives, and these are actually on your derivative sheet as well. Either now or later, you'll want to make sure that they get put in there so you'll have them for your test. If we have the function a to the x, then the derivative is a to the x ln a. So you see part of that e to the x rule, right? Derivative of e to the x is e to the x. Derivative of a to the x is a to the x. But you also get multiplied by the natural log of a. And if you look back, let me see if I can find it on my screen. If you look back at how this was defined, you can see why. A to the x is e to the ln a of x. What's the derivative of a to the x? Well, it's the derivative of e to the ln a of x. What's the derivative of e to the power? It's e to the power. What's the derivative of ln a times x? Well, that's a power rule, right? Or I'm sorry, that's a chain rule on the inside. And the derivative of a coefficient times x is simply the coefficient. So that's where that's coming from, is the definition of how a to the x is defined. We have one more. We have the derivative for the log. So if we have f of x equals log base a of x, then the derivative, f prime of x, equals 1 over x. That's part of it, right? Because the derivative of natural log of x is 1 over x. And then you have to multiply by ln of a in the denominator. I'm not sure if your book, because I doesn't really matter, but some books will also put the ln of a before the x instead, as like a coefficient of x. It's the same thing, so either in front or behind. Same thing up there on the rule number 1 that I just wrote in. So if I just told you a bunch of rules, that means we better use them, right? Yeah, we are. We're going to do a couple examples of derivatives. All right, so here's our first one. We have 2 to the t times t, t to the 2 times 2 to the t. I know, exactly. So I always like these because you have to really stop and think, because these both look like powers. But where the variable is changes everything. And you guys saw this on one of the e to the x ones that we did on the board, didn't we, Emily? And I said, wait a minute, you're using the wrong rule, right? This is an exponential rule, not a power rule. So you have to be careful which rule it is that you've got based on where your variable is located. All right, so we're doing a derivative. Please make sure that you're notating what you're doing every time. This is the derivative. Don't just put equals, because that would mean it equals the original function. This is not going to be equal to the original function. This is the derivative of the original function. All right, so I think that most of you like to take the derivative of the first part first.
After we notate
Yes.
the derivative right there, can we just do equal sign
Sure.
under that?
Absolutely. You betcha. All right, so what is the derivative of t squared? 2t. You guys like that rule. Now we need the derivative of 2 to the t. I'm sorry, let me say that again. Let me rewrite the 2 to the t as the second part. I'm getting ahead of myself. And an addition sign. Then we need to rewrite the t squared. And we need the derivative of 2 to the t. So what is the derivative of 2 to the t? 2 raised to the t power. Don't tell me it's t 2 to the t minus 1. That's the power rule. This is not a power rule. This is an exponential rule. What does it say I'm going to do? Two to the t, natural log of 2. That's exactly right. Very good. This is all the calculus. Everything after this is algebra simplifying, right? What do you see common to both terms? 2t or 2 to the t?
2 to the t.
2 to the t. I think I should have used 3s. 2 to the t is definitely in both terms. Anything else? T is as well. I think that's it. So if I have the 2 to the t, that removes this component, and I removed the t, which means from the first chunk, all I'm left with is a 2. I have also removed this 2 to the t, and I've removed one of these t's, right? Which means one of them's still left. T ln 2. One other word of caution, I hate t's because my t's, I always put curls on the bottom of them, and sometimes you guys don't. So just be really careful if you're doing t's. Absolute values kind of pose problems as well. Sometimes if you're doing a t, make sure that it looks different than your plus signs.
Can I change them to like X's? Or
Yeah,
something?
that's fine with me. I don't care if they're in X's. Yeah.
Thank you.
And then we're actually done with the problem, right? There's no more simplifying. It's all done. All right, letter B, I guess. All right, so you guys encountered some that looked like this when we did logs before, but we did them with natural logs. This one doesn't actually have a number down beside it. Any idea what that number then is? It's a 10. When you don't see a number down beside the log, it's called a common log, and it's a log base 10. Not that it affects anything you're doing at this exact moment, but it will affect your derivative. I want to do something, though, before I take a derivative. What do you think I might want to do? Split it up. I would. In fact, I want to split it up even more than you know. I bet that you know one thing I want to do. What do you want to split up?
Make it log x squared minus 1, then minus log.
That'll work. And if you want to go from here, you can. We can go from here. There is one other thing that we could do, and just because I want to give you guys the flavor of how to handle this, another possibility. Is there anything you can do to change x squared minus 1? An algebra kind of idea? How's it factor?
X plus 1, x minus 1.
And then I can actually rewrite this one more time as log of x plus 1 plus log of x minus 1 minus log of x. If you don't recognize that there, it's not a big deal, right? I mean, you can take the derivative of the chain rule. It's not that bad with the one above. But this means that I won't have any chain rules. And I think that's even better. So, yeah. All right, notice my equal signs are carrying throughout this, right? These is all equal to the original function. I have yet to do any derivatives, but I'm about to. So we're going to do a derivative now. So this is going to be y prime. These are all added together, which means I can take each of their derivatives one at a time. So what is the derivative of log of x plus 1 going to be? It's going to have a 1 over, right? Because it's logs. 1 over what? X plus 1 times what? Do you remember the other part of this rule? Close. ln of 10. Yeah, ln of 10 will be in the denominator with it. It's the natural log of whatever the other base was, and this other base is 10. Right? We said that this is understood to be base 10. All right, so that's the first one. What's the second one's derivative going to be?
Does that come from like a chain rule?
Yes, it does. And in fact, I'll show it to you real quick since you asked. Back over here where we defined these, this is what we defined this as, right? So ignore this piece. What's the derivative of ln x? 1 over x. This right here is just a number. It's a coefficient, so it's the coefficient rule. So this component of it, that's that ln 10 that we're working on this problem at, that's where that's coming from. Yeah. All right, what's the second derivative? Good. And then the last one? Perfect. So the derivative was easy, but then the algebra at the end is messier. That's what happens sometimes. So as I'm looking at this algebra, I'll just use black. I need to have every, oh, and I messed one up. This one was, nobody told me I messed it up. That was natural log of 10, not x. All of these have an ln 10 in them, right? So that's part of the common denominator, so that's good. But they all need every other component. So the first one is going to need an x and an x minus 1. The second one is going to need an x plus 1 from the first term and an x. And then the last term is going to need an x minus 1 and an x plus 1. And then my denominator is going to have all of them. I'm going to have x.
Why isn't that one minus?
It's supposed to be. Thanks, Emily. There we go. So my denominator is going to have an x plus 1, an x minus 1, and an x. And I'm just as happy as anything to leave that denominator in factored form. There's no reason to simplify that. I am. What am I missing, Cameron? Yeah, I am. All right, let's simplify that numerator, though, because that requires some simplification. All right, I have x squared minus x, and then what?
Plus x squared plus x
Good?
minus x squared.
Is it going to be minus 1 or plus 1? It's going to be a plus 1. How come?
Oh,
Because this minus that Emily told me I had to put back in, right? Yeah. So this is x squared minus 1, and then I'm changing both their signs with that negative. So some of this goes away. What? I think this x and this x can go away, right? One's plus x and the other one's minus x. And then one of the x squareds can go away with this negative x squared. So I think all that I have on top actually is x squared plus 1. The denominator didn't change. It's x plus 1, x minus 1, x, ln 10. So my final solution would be x squared plus 1 over x plus 1, x minus 1, x, ln. Pretend like that 10's right next to the ln. I'm out of space, I'm sorry. Don't be tempted to think that this x plus 1 and this x squared plus 1 simplifies, because they don't, right? X squared plus 1 is not factorable, not in the real numbers, and we're doing calculus in real numbers. So I can't in any way, shape, or form get it to look exactly like x plus 1 to actually cancel out a factor. Is that good? Any questions on that one? Well, what's weird about this one? The exponent's a little different because it looks like a fraction. What else is weird?
And find dy dx.
We are going to find dy dx. That just means derivative, right?
Yeah, but the y. Wait, never mind.
it's in respect to x.
Mm-hmm.
It would be weird if y was on the bottom.
That's true.
Is it because it says logarithmic differentiation instead of implicit?
Is it because it's
It is
X?
going to be implicit after we introduce logs. That's part of it, but that's
Is
still
it-
not,
Is it X raised to the X?
yeah, that's the weirdest part. I've got two x's involved, right? I've got x in the base, and I have x in the exponent, and that's different. And without logarithmic differentiation, you don't have any way to handle that situation. Because what rule would you use? Do you use the rule where x is the exponent, or do you use the rule where x is the base? And the answer is, yeah. What do I do with that, right? I mean, I have both going on here. So I do need logs, because I need to be able to get the exponent and its base separated. Okay? And logs will allow me to do that. So if I do this with logs, I'm going to put a log on both sides. And we've seen logarithmic differentiation, at least on the board once before this semester. I'm going to take the log of both sides. And we're going to use natural log because it's as good as any. It doesn't matter which log we use. I don't have to write as much if I do ln x as if I do ln, or if I do log x, right? Yeah. Why do I like ln's on the right-hand side of this? Because I can bring that down and simplify it. So my 2 to the x can come down to the front. Notice I've not taken any derivatives yet. So far I've done no calculus. But I'm about to. Because the right-hand side is now a product, isn't it? Well, I can deal with products till the day is long. Yeah? Products are not a problem. You started those last year. Okay? So ln y, what is the derivative of ln y? It is 1 over y. And then what? No. dy dx. The ln 10 comes into play when we have log base 10 in the problem. We don't have that. We just have ln. Okay, so we have dy dx, which is good because I'm supposed to find it. It better show up in the problem at some point, right? Yeah, because it's not there at the moment. Now I need the derivative of 2 over x ln x. You can handle the 2 over x in a couple of ways. If you want to handle it straight as it is, you can handle it as a quotient, 2 and x, right, to take its derivative. I prefer to do this with it. I prefer to rewrite this as, yeah, I'm going to do it that way, as writing it to the negative 1. Because then it's a power rule. I don't have to have a quotient rule, and I kind of like that a little bit better. All right, so let's do it from this perspective. So the first thing I'm going to do is I'm going to take the derivative of 2x to the negative 1. And what is the derivative of 2x to the negative 1? Good. And then what do I do? ln x. Am I done? No, but I'm half done, right? So I'm going to do plus, and I'm going to rewrite the 2x to the negative 1. Now I need the derivative of ln x, which is 1 over x. Now, if it helps you to see this rewritten, I'm going to write it over here. This is actually 1 over x squared, right? And this is 1 over x right here as well. So I'm going to rewrite that cleaned up a little bit, but here's 1 over y dy dx. I have, the 2 is not in the denominator, although it sort of looks like it the way that I've got it written. This is negative 2 on top, x squared, ln x, sorry, x squared on bottom, and then ln x to the side. And then over here I have plus, and I have a 2 on top. And what's on bottom? X squared, actually, right? Yeah? I have this x, and I have this x. So x squared. Happy day, the denominators match. I also have one other thing I have to handle here. What is it? Got to move the y. So this will be dy dx. Oops, let me change that back. I can combine these two fractions on the right-hand side. So this is negative 2 ln x plus 2. It's over x squared. And then I'm going to multiply by y. And in multiplying by y here, the y is actually equal to x to the 2 over x. That doesn't simplify with the x in the denominator. I guess you could simplify it some. You're not going to see that traditionally done because one of them has an exponent that's a number and the other one has an exponent that's a variable involved. So your probably best shot to write this is to notice, first of all, also on top, you could pull out a 2 if you wanted to, right? So let me write that as the 2 pulled out. So we'll write this as 2 over x squared. And then I pulled out a 2, and I was left with negative ln x and plus 1, or you could do 1 minus ln x, and then x to the 2 over x. So some variety of that's the best you can really do. There's no other simplifying, common simplifying that would be expected. All right. But if we do derivatives, we also got to do antiderivatives, don't we? So one thing you'll notice, though, is that there's only one antiderivative we're going to do. So tell me first what I'm going to fill in on the first 2 blanks. You guys know. What am I filling in? A is greater than 0. A is also what? It's an element of the real numbers. And it can't equal 1. And if that's the case, then if we have the function little f of x equals a to the x, and we want to find its antiderivative. Well, think about the e to the x rule. What's the antiderivative of e to the x?
E to the x.
E to the x. So the antiderivative of a to the x is going to have an a to the x in it. Agreed? Mm-hmm. You bet. Now think for a moment what the derivative rule was for a to the x just a moment ago. The derivative of a to the x was a to the x times the natural log of a. Well, when we do derivatives versus antiderivatives, things get reversed. So what do you suppose will happen instead of multiplying by natural log of a?
Divided.
You divide. So this becomes, and it gets divided by ln of a. Again, you don't have to memorize that rule, right? But you should be able to have a feel for where it's coming from, both from the perspective of e to the x and from the perspective of the a to the x's derivative in reverse. So let's take a look at a indefinite integral. I like intermixing power rules and exponentials. Keeps you on your toes. So, first, the easy part. What's the antiderivative of x cubed? Oh, you know what? I left something off. What did I leave off back here? What did I leave off? Plus c. I did. Make sure that plus c gets there. I'll tell you that antiderivative gateway or basic skills quiz that you're going to have here in a couple months, I had a student who would have gotten a perfect score on it the first time that he took it, which means bonus points, right? But he forgot plus c on every single one. Yeah, it's important.
I always miss that on my homework.
Don't miss it.
I had to go back and like rewrite it.
All right, so what is the antiderivative of x cubed? This is not a trick question.
Or 1/4.
That's right. 1/4 x to the 4th or x to the 4th over 4. This is the plain old power rule that you guys have been doing for, at this point, quite a while. Right? It was probably one of the first antiderivative rules you learned. That 3 to the negative x, however, is a new antiderivative rule. Slightly. All right, so 3 to the negative x. Well, first of all, pretend like the negative's not there. Just ignore the negative for me, okay? 3 to the x. What would the antiderivative of 3 to the x be?
3 to the x times 1 over natural log of 3.
Would be 3 to the x divided by natural log of 3.
Right. So the 3 to the x is there. Notice I already wouldn't put the negative on there. I kept the negatives the same. We'll deal with him in a minute. And I divided this by ln 3. How do you suppose that negative gets involved?
It's negative. What makes it negative?
It's like a chain rule, right? Or a u substitution. And whenever you have negatives involved, they end up giving you a negative value. Because if you really did this u substitution and you let u equal negative x, what does du become? Negative 1 dx, which means I end up getting another negative 1 in the problem. It's really not worth doing a u substitution for every time. When you've got a negative exponent, it just makes the whole thing negative when you're done. That component of it anyway. What's missing? Plus c. Thank you. So I think we can clean this up just a tiny bit, maybe. You can leave it as 1/4 x to the 4th, or you could write it as x to the 4th over 4, whatever your preference. And then I'm going to put a negative 3 to the negative x over ln 3 and plus my c. I really don't need to combine the x to the 4th over 4 and the 3 negative x over ln 3 because the original equation that I was given, the original expression I was given, wasn't combined, was it? It wasn't. So I really can leave them separated here, and then that's just fine. How about this one? I just told you a minute ago I didn't need to do u substitution, but here it would probably be a good idea. What do you think you might let u be here?
3 minus x.
That's part of it.
Squared.
Yes. Any idea why I have to let the squared be in u?
Because it would be something squared, or something.
I would still have a squared in the exponent, right? If I just let it be the 3 to the x, I'd have u squared as my exponent. Well, the rule isn't anything in the exponent but plain old x. Make sense? So I've got to eliminate all of that exponent with what u is equal to. But that's actually really good because what's the derivative of 3 to the x squared? Sorry, 3 minus x squared.
3 minus x.
That's part of it. I'm going to have a dx.
Negative 6 minus 2x, or plus 2x.
I almost left no space. There's a negative 1 in there. Why do I have a negative 1?
Because you take the derivative of what's inside.
Yes. So Dylan, you tried to take the derivative of the 2 and the 3 minus x. We just need the derivative of what's inside the parentheses only. So the derivative of what's inside the parentheses only would be negative 1, right, from that negative x. And if you take a look, the 2 and the negative 1 are not in the original problem, but the 3 minus x is. So I can rewrite this as negative 1/2 du equals 3 minus x dx. All right, so let's take this antiderivative. I'm going to rewrite it, which means I'm not taking an antiderivative yet. I'm turning it into u. What goes in front is negative 1/2. I have my script s for the integration symbol. What goes next? To the u du. So this piece and this piece get replaced with the negative 1/2 du, right? Because those pieces are all equal. And then the 7 is still there with the exponent, 3 minus x squared, being replaced by the exponent u. But then it turns into one of the rules. I mean, it is the rule that I've just dealt with. So I've got a negative 1/2. What's the antiderivative of 7 to the u?
Over ln 7.
Right.
Plus c.
Plus c. Good. And once I substitute this back in, I'm going to have negative, well, I'll put the negative in front. I have 7 to what power? 3 minus x squared. What's my denominator?
2 ln 7.
And then I have plus c. This is finished. This is correct. I want to show you one other step that you might see the book take that would also be correct. You could see this written as negative, and then the 7 to the 3 minus x quantity squared. That's a 2. And you could see this written as ln 49. Any idea why that might work or where that came from?
Because you can move 2 in power.
Yeah. You could turn this 2 that's a coefficient into the power here. There's no reason to do that, but you could do that and it would be equally as simplified. Neither of these is any better than the other. But I want you to recognize of how an alternate form that you could see somebody do, or if you're comparing your answer to somebody else's. All right. I mentioned a formula earlier. Well, I showed you a portion of a formula, and Cameron remembered what it was, or mostly. And the formula actually looks like A equals P times 1 plus R over N to the NT. Just a reminder is how those pieces go. The formula that we just saw, where we were solving for it, that's what we were doing, didn't have a number on the outside of that parenthesis. And the reason it didn't is because what we were solving for. But P is a principal. It's the amount of money you put into an account. So if you go to the bank and you put $5 in there, that's your principal, $5. R is your interest rate. You always have to turn interest rate into a decimal. So if you had a 30% interest rate, that would be the decimal 0.3. But if you had a 3% interest rate, that would be a decimal 0.03. Your time, T, is always given in years. So if somebody tells you something about 18 months, you don't put 18 in. What would you put in? 1.5, because 18 months is the same as 1.5 years. N is, let's say first. I even left N off. A is the amount after T years. That's how much is present. So if you put the account into play right now and you left it there for 5 years, this would be the amount that it's worth in 5 years. And then it says, I left it off because I wrote it down here. And for continuously compounded interest, we have a different formula. Now, the one thing that's different here between continuously compounded is the N. So the N here is actually the number of compoundings per year. So you'll see interest rates given quarterly. That would mean how many times a year? 4, as in 4 quarters in a dollar. Monthly, 12. Daily, 365, and so forth. Yeah. What's that? Yeah. We'll use 365 in our problems. Yeah, but yes, you're correct. And then we have another interest formula. And so if we have continuously compounded interest, this is A equals PE to the RT. And money doesn't actually compound continuously, okay? So I get that. But you can model this or model different things that do compound continuously by the same formula. So that's where that's sort of coming into play. So you're going to have 1 or 2 application problems with interest in this section. You're also going to have some application problems with a logistic function. You may or may not have ever seen the logistic function before. So if you kind of cover up, let's cover up this half of it over here, and you just look at that portion of it. Do you know what that looks like? The graph of that we've seen in class recently? Looks like an exponential, right? This is the idea of something starting out exponential, right? So imagine you've started a wildlife reserve and you introduce deer into the wildlife reserve. Initially, because they've got plenty of food and plenty of space and whatever, they multiply very quickly. Okay, that's great. But eventually what happens is you get a lot of deer in your wildlife reserve. Food becomes scarce. People hunt, or the deer leave for other places that are more, spread out or whatever. And then you've got some sort of a leveling off thing going on. That leveling off is called the limiting value or the carrying capacity. And I want to show you the general form for this equation. So this equation equals, and it's L for the limiting value over 1 plus A e to the negative bx. And in this formula you see hidden, kind of, an exponential. Right? That's giving you that exponential sort of shape at the beginning. You also notice something interesting. The graphs here that I've drawn, the first one says this is where b is greater than 0. But look back in the equation. If you put a b value that's positive into the equation, what happens to your exponent? what sign will your exponent have if b is positive? It'll be negative. So when you have a negative exponent, you end up with a curve that's increasing, right? Increasing curve with a negative exponent. So this right here means I have a negative exponent. And if the b value is negative, what's my exponent? It's positive. So a positive exponent ends up giving you a decreasing curve. Sorry, it shouldn't have decreased that far. And notice, of course, it's leveling off on the x-axis. And again, you're going to have some applications with these. What you're going to have applications doing, if I'm remembering correctly, are going to be solving equations with them. So they're going to have you solve for x, in other words, and they're going to give you some of the other details or whatnot.